All right, and if you stepped through func3 plus 4, which again is not the last store, but rather the last movement of the frame pointer, this is what you should have seen. And indeed, you start to see what looks like a pattern here, and it appears to be the extension of the pattern we learned before. So we've got the main, which stores off the way to return back out of main and the frame pointer as it existed at the time that you got into main. We've got main's frame, we've got func's frame, we've got func2's frame, and we've got func3's frame. And the key difference again being that func3 is a leaf function. It calls no other functions, and therefore it doesn't look like it needs to save off the return address. It can just keep the return address in the RA and ultimately return back. So our takeaways from this is that the pattern holds. The return address is not saved to the stack by leaf functions, but it is for interior functions. Now I want to actually kind of show you what's really going on with the frame pointer usage. So let's start here. We're here somewhere inside of func3. The stack frames have grown to the point where func3 has a frame. Frame pointer points here, and even back in the call one function no args, we saw that it looked like the convention was frame pointer -8 to get the saved one for leaf node, and frame pointer -10 to get the saved one for other ones. So let's see that concretely. Frame pointer -8 gives us a saved frame pointer. This is a pointer, so where does it point? It points to 8F0. So this points up to here, 8F0, that's the previous location of the frame pointer before it was moved down. And this, if we do a -hex10, because it's an interior node, not a leaf node, -hex10 gets us down to here, another saved frame pointer. Where does that point? Points up at 900. Then let's do another -hex10. That brings us down to 8F0. We find another saved frame pointer. Where does that point? Points up here at 910. We do another -hex10. That points down here. It has a saved frame pointer. Where does that point? A98 is where the frame pointer pointed when we first got into main. So this points all the way back up to there. And this, you're now starting to see how the linked list exists. It's not exactly as clean as it is on some other architectures where the frame pointer literally just points at the saved frame pointer. And furthermore, because of these conventions about sometimes the return address is saved on the stack and sometimes it's not, we've got this discrepancy of the leaf node versus the interior nodes, but still you can see the general idea of how something like a debugger could walk backwards and figure out what frame we're in. So GDB has a command bt for backtrace the call stack, and it would show you something like this. If you're sitting there in func3 and you run bt, it's saying, hey, you're in func3 now. But if you returned, you would return back to func2, and func2 would return back to func, and func would return to main. Or another way of saying it is that main called func2, called func3. So how does a debugger figure this out? Well, the first way that it figures out that it is currently in func3 is simply looking at the program counter and saying, here's the program counter. Is it between the boundaries of some particular function based on the symbols that have been compiled into the executable? Yes, looks like it is. It's within the bounds of func. But then how does it know that it would return back to func2? Well, if you're currently in func3, then the RA register should hold where you're going to return back to. And the RA register holds 5s, 6, 4, 8, and that is indeed what the bt command says. It says 5s, 6, 4, 8 is where you would return back to get to func2. Then how does it know that func2 returns back to func? Well, there now it starts to use the linked list that is on the stack, and it goes and it searches and it finds the first saved return address on the stack, and this is 5s, 664. And so it's saying func at address 5s, 664 is where you would return to if you were returning from func2. And same thing again, how do you get back to main? It goes, it searches the linked list, it finds the next saved return address, which is 680, and it knows 680 is inside of main. That is where you would return back to. Now, of course, it could keep searching and it could say like, okay, well, main is going to return back to whatever this thing points to, which is something like start. But in general, they don't show that because in general, programmers don't want to see where their main function returns back into system included code. You just say, I wrote code from main, and that's all I really care about. So yeah, this is how something like the backtrace command can utilize this linked list, walk backwards, find things on the stack like saved return addresses, saved frame pointers, and so forth. Now, earlier in the class, I gave you this example of what's the frame pointer and what's its point when we first encountered it, and I said it's going to matter once you start having many functions that there's going to be a linked list. And I gave you a very sketch outline. Now we know things about local variables, now we know things about return addresses, now we know things about frame pointers. So I can fill in this code just by sort of eyeballing it and understanding what's going on. So the first thing main would do is it would allocate space for a frame, and the compiler would allocate space appropriate based on what it knows about what it needs to save for return addresses. Is it going to call another function? Yes, it is. Okay, it needs space for return address. Is it going to save the frame pointer? Yes, it is. It was compiled with saving frame pointers, so it allocates space for that. And does it have local variables? Yes, it does, so it's going to allocate space for that. So space is allocated. I'll just point out that because there is a single local variable, we've seen thus far that, space for local variables is allocated in hex 10 sized chunks. There's only an int, so therefore necessarily there's going to be overallocation. There's going to be uninitialized space for alignment. And so when you get in here, the first thing that this code would do, based on just, that previous assembly for that other code, we know the first thing it does is that it's going to allocate space, then it's going to save the return address, then it's going to save the frame pointer, which will point up to wherever the frame pointer currently points, and then it's going to move the frame pointer down. Based on that diagram we just saw, we get the sense that the frame pointer is going to be, if there's a return address, it's going to be frame pointer -10 to get the save frame pointer. So essentially, it's kind of like the frame pointer is pointing just outside of main's frame. So it gets moved down to here. There was the space reserved for int c. It's not actually going to be set to anything yet until this foo returns, but we'll just place it on our diagram to say, yes, there's going to be an int c. So stuff in this frame, return address, frame pointer, local variables, and padding due to needing to have alignment of hex 16 boundaries. Then when main calls into foo, foo's going to do the same thing. It's going to allocate space. There's going to be too much space because there's only a single local variable b. It's going to save the return address because it calls to another function bar. It's going to save the frame pointer, which points at wherever the frame pointer currently points. It's going to move the frame pointer down. The frame pointer is kind of pointing outside of foo's frame. And then there was that space for int b. And in this case, b is set to something upon initialization. So there would be an actual value in there. Foo calls to bar allocates stack frame space. There's going to be some uninitialized alignment space both for the local variable a, and because we now know that leaf node functions don't bother saving the return address, but they still have to keep things aligned to hex 16. So save only the frame pointer, move the frame pointer down, and allocate space for int a, do the ultimate calculation based on the input arguments, set the value to a, and then print something, and it's time to return. So what happens upon return? Well, the thing is going to move the frame pointer back up to where it used to be, and then it's just going to deallocate all of the stuff for the frame by just changing the stack pointer back to where it used to point, which is right here. I should have perhaps included the stack pointer on this diagram, but oh well. So then bar just returned to foo. Foo is going to say, okay, well, I'm just going to return immediately as well, back to main. So what does it do? It moves the frame pointer up to where the saved frame pointer says it used to point, and then it just deallocates all the stack space by adding to the stack pointer. And once more, main just got the return value from foo. It's going to store it into C, so now C would have an actual value based on this calculation. But last thing it does, moves the frame pointer up to wherever it used to point and deallocates the space. So that is now actual detailed look at what's going on with frame pointers. We now know stuff about what's on the stack. We now know about how frame pointers used to create a linked list, and that's cool.